Today we have a continuation of our lesson that involves impulse equals change in momentum. And its comparison to the idea of work equals change in energy. Now you've seen this before, but it's a great illustration, kind of the synergy of the topics. So what happens over here with work equals change in energy can be mirrored with what happens over here with impulse equals change in momentum. And today we're going to introduce a new part of that synergy, and actually a very important part of that synergy with respect to the AP curriculum. So let's just recap a little bit. If we think about this basketball over here sitting on the desk, the basketball has no mechanical energy with respect to the desk. So if it's stationary, the energy is zero with respect to the desk. The height is zero, so there's no gravitational potential energy. There's no spring involved, so there's no elastic potential energy. And since it's stationary, there's no kinetic energy. The only way to change that energy is to do work on the basketball. So if I wanted to get it moving, I'd have to exert a force over a distance, perhaps horizontally. I change the gravitational potential energy if I exert a force over a distance vertically, and so on. So when we do that work is the product of F delta X, we can change energy. And that change in energy can come in the form, theoretically, of any of the three types of mechanical energy. Now, obviously, we know there's no spring involved here, but in various circumstances, there could be / would be. We can take the exact same ideas and bring them over here to the idea of momentum. If I have that basketball and that basketball is stationary, the only way to change its momentum, and momentum being m times v, the only way to change its momentum is to give an impulse to it. Well, impulse is the product of force and time. That impulse causes a change in momentum. Now, what are we going to add to that today? We're going to add a graphical idea to that today. If I take and graph force as a function of location, we're going to be able to do something with this graph. Let's make the graph as easy as possible to start with. Let's say we've got some number up there. Could be 10 or like whatever, but I'm trying to avoid putting a number up there. Well, if the graph of force times distance looks like that, then there's a constant force over a total distance. Let me put a number in there for just a second. Let's say this is 10 newtons and this is 10 meters. Well, if we exert a force for 10 newtons for a distance of 10 meters, then we've done 100 joules of work. So the amount of work done is 100 joules, which means we can change the energy by 100 joules, whether it is kinetic or gravitational potential or elastic potential or whatever. Now again, I'd like to get rid of these things because I don't want you focused on the numbers. I want you focused on the ideas. So we're taking F and multiplying it by delta X. That's this thing. But it doesn't make much sense if instead the force is a constantly varying force. So before, when I had this constant force, I just took the value for force and multiply it by its change in distance. Well, if this number is again 10 or 100 or whatever, this graph is clearly illustrating to us that we're not pushing with this amount of force until the very end. So we're not pushing with 10 newtons of force. I go back to the number again. For an entire 10 meters. Instead, I'm pushing with less than 10 newtons for most of the distance, and I don't reach the 10 newtons till the very end. So it doesn't make much sense for us to calculate work the exact same way. And in fact, we can't, because in reality, this is the average force being exerted. And if this force down here is 0, and this force up here is 10, in this particular case, it's relatively easy to see that the average force would be 5 newtons, and that's what we would use to plug in here. 5 newtons times 10 meters would give us 50 joules of work. That's relatively straightforward as well. However, that becomes even more difficult if we have, a force that varies but doesn't vary, uh, steadily. Now all of a sudden it becomes very difficult for us to figure out what this average force is. So now we've got to go to some different ideas. And that different idea is area under the curve. Now, in reality, we could have done that area under the curve for the other ones as well, and we'll show you that in a second, but you'd have to do that in this particular case. So the work done for so work is equal to the area under the curve for an F versus X graph. Which means all these changes in energy that are equal to work can be calculated by taking the area under the curve. Now, why is the area under the curve for an X versus or F versus X graph equal to the work? Well, look at, how do you take the area under the curve? Well, it's easier. Now we have to do the area under the curve for something like this because we can't find this average. And oh, by the way, next year when you do calculus, the area under the curve is synonymous with a calculus term called integral. But for our sake, look at, how is it the area under the curve is equal to the work done? Well, look at that. What shape is under that curve? It's a rectangle under that curve. How do you get the area of a rectangle? Well, you take its height and multiply it times its base, or its length times its width. Excuse me, when you're doing that, you're taking F times X. Well, what quantity is F times X? It's the work being done. Likewise, if I go back to my second one, what shape is under there? It's a triangle. Well, what's that? That's 1/2 base times height. In reality, when we use the area under the curve idea, we're really actually just taking F and multiplying it times delta X. But you will constantly see graphs of F versus X in our AP Physics 1 course. The split second you see a graph of F versus X, this needs to be your first idea, that the area under the curve for that graph must be equal to the work, which is also equal to the change in energy. Now, everything we've had over here has had its partner over here, and it's the exact same thing. If you see a graph of F versus T, no matter what that graph is, the area under the curve for that graph, so the area under the curve of an F versus T graph is impulse, J. Well, what do we know about J? Impulse is equal to the change in momentum. So the area under the curve for this graph is equal to the impulse. Impulse is equal to the change in momentum. The area under the curve for this graph is work. Work is equal to the change in energy. Our synergy holds true even when we put graphical stuff involved here. Anytime you see this graph, automatically you think this. Anytime you see this graph, automatically you see that. And guess what? These graphs come up all the time. Now, one last thing before we leave you today. This idea of area under the curve is a little bit misleading. I don't know if misleading is the right idea or right term, but I got to clarify something. Area under the curve simply means the area between the graph and the axes. For instance, if we have a graph that looks like this, momentum versus, I'm sorry, not momentum, force versus time, and the graph spends some of its time up here in the positive and some of its time down here in the negative. These are positive forces and these are negative forces. So as we know, force is a vector quantity, and the plus and the minus would dictate direction. The same thing could be true over here if I replaced, this t with an x. It's the same idea. So the area under the curve for this section over here, is kind of just how we dealt with it right there. But the area under the curve over here is that section highlighted in black. It's actually above the curve. So what do we have here? We have a positive force. Well, guess what? Impulse is a vector quantity as well, and so is momentum. So a positive force would lead to a positive impulse, which would cause a positive change in momentum. But as this tries to add to the momentum in a positive direction, this is under the axis, which means the area under the curve is a negative area under the curve or a negative impulse, which would lead us to a negative change in momentum. So if this object started from rest, this portion up here would act to speed the object up, followed by a region over here that would act to slow the object down. So we have these pluses and minuses depending on where you are within the axes. So your pluses and minuses for area under the curve work. But I can't emphasize enough, and the main point of today is as soon as you see this graph, your mind goes to area under the curve, and that's work. And work is the change in energy. And as soon as you see this graph, your mind goes to impulse is the area under the curve, and impulse equals the change in momentum.